This is Statistics 243 for Monday, or Wednesday, September 24th. This should be about the 11th class of the semester. Okay, let's get started. I don't have too much more I want to say about this unit. I want to sort of check in with you guys, see if you guys had any questions about the debugging tools. Then I'll have a few more fairly brief comments, and then we'll switch over to Unit 6. But I think, as I mentioned, for Monday, I'm going to send out an announcement soon about this discussion of good practices for coding and for reproducible research, and we'll discuss that on Monday. And so as part of that, I will ask you to look through the parts of this section that we haven't talked about here in class. Okay, so last time we went through a few of the R's debugging tools, which have some similarities to debugging tools in other languages. And most of you hadn't actually seen debugging tools before. So I'm particularly glad that we did spend some time on that. Actually, I was listening in on a conversation of a couple postdocs that I work with, and they were commenting on the fact that until they started on a project that we're all working on together during grad school, they never saw debugging tools, and they were just putting print statements into their code. So you're not alone if you hadn't seen it before, and so I'm glad that you're seeing it now, fairly early on in grad school. So I just wanted to sort of have a moment where we could touch base and see, was there anything particularly, did people find there was anything confusing or that wasn't clear about how you would go about using some of these tools, or were there things that people thought was particularly useful or not useful in what I talked about? Yeah?
So I thought it was really interesting and useful that you could put like the debugger into functions over which you don't have control,
Yep.
and view the values of variables in the call stack and whatnot, because that's really difficult to do in other contexts and other languages. So I thought that was really neat.
Yeah, so that's interesting. I've used debuggers in C, but I guess in other compiled languages, oftentimes things are not set up so that you can actually go into code that somebody else is providing to you that you're linking in. But in R, everything is everything is accessible. So yeah, thanks. That's a good perspective. Any other comments or questions that people had? Okay. Let's see. So I'm not gonna say too much here. I have a bunch of stuff in here about sort of tips on good practice in terms of what your code should look like, so that it's easy to read and easy to debug and easy to decipher. And I will let you read through that on your own. But I will just quickly pull up, and I put an example in the repository I have a file in here now called bad code and a file in here called good code. And I thought I'd just pull those up briefly. And part of what I want to emphasize here is just that it really does make a difference when you're trying to understand what you're doing and when other people are trying to read your code. And part of what I want you guys to be doing in this third problem set and going forward is being mindful of some of the things that I'm saying in this unit in terms of good practices for your syntax and your coding. And as Jared is doing the grading, some of the things that he'll be taking account of when he does that is the structure of your code, the syntax, how you lay it out, is it easy for him to see what you're doing, and those sorts of things. Yeah, Daniel?
So to a degree, editor overwrites a lot of the formatting in your code chunk.
Yeah, that's a good point. Yeah, that's a totally fair point. You are submitting the code with the chunks as you've written them, just as a LaTeX or an RMD file.
Right.
So we can still see that, but that's a good point.
It's tidy to make sure the lines don't go over. It'll deformat your indentation.
Yeah, no, that's a good point, and something that we should be aware of when we're thinking about what you guys are submitting. But
Attaching the plain text file, or just keep using.
well, it should. I mean, no, we still want you to use that. There are sort of competing objectives here, but I guess what I would say is even if you have tidy in there, you're submitting the underlying, say, LaTeX file to your repository. So all the formatting there is going to be whatever you put in. Yeah. So let me just see if I can open this up quickly. And this is just going to be sort of a quick visual demonstration of this. So I just want to I want to throw up what I am calling bad code here. Does anybody remember off the top of their head how to make this bigger?
Control plus.
Control plus. Command plus. Great, thank you. So this is, there are some parts of this that are not terrible, but just in terms of sort of the layout here, I haven't done anything with spacing. I haven't done anything with introducing additional white space. I haven't put any comments in. I haven't written the code such that there's a block of code that does one discrete thing and another block of code that does another discrete thing. So I just wanted to sort of assault you with the awfulness that is this formatting, and say, you know, when you look at this, it's really hard to figure out, you know, sort of what are the things to focus on, what's going on in any given line of code, where are the key chunks of the code that might be doing different things. Okay, so don't do this. You know, on the plus side, it does look like in this particular example, this is code from a project of mine from a couple years ago. I deliberately made it worse than it was to start with, so this is not how even a couple years ago how I wrote my own code. You know, on the plus side, at least the names of objects look like they're fairly informative names. So there are things in here that are not terrible. There are some features in here that are reasonable. But I want to compare that with something where I took some time to try and format it in a reasonable way. And there's still things in here, I'm sure, that are that could stand for improvement. But just as a demonstration, so here I have at the top of this file, I have some information about who wrote it and what this code does. There are other ways to store sort of information about what are the open issues with your code, but in this case, I just have a list of sort of what are the things that I still want to deal with in this code that still need to be addressed. And then I have a little bit of a chunk of code here that is an example of how you would actually run the code. So the code down below here is code that functions I've written to do particular things. And then up here I just have some demonstration code of how I would actually go about using it. So that's that. And then in here I just want to point out the fact that I'm interspersing comments here. I'm using white space in terms of lines to mark off different pieces of where different pieces of code are doing different things. I'm liberally using white space in terms of just spaces here so that it's easier to see the pieces of any given line of code. See if there's anything else worth pointing out here. I think it's usually good practice to use true and false totally written out instead of using T and F, so it's easier to see. Otherwise the T and the F can sort of get lost amidst the rest of your code. It'll work, but it's not quite as easy to read. And then the way that I've written this in terms of using squiggly brackets is fairly standard in terms of what's considered good practice in terms of where to put a new line relative to an if and an else statement, and where to put new lines in terms of relative to the squiggly brackets around if statements and for statements and function definitions and things like that. So I don't have too much more to say about this. I just wanted to throw this up as a demonstration. But do go ahead and look through the notes I have in the unit. And as you're thinking about writing code for the next problem set and forthcoming problem sets, keep these sorts of things in mind. And you don't have to do it exactly this way. I'm not saying that you have to use exactly the style that I use, but just to think about these issues and develop. It's also good to develop your own style where you do things consistently in your own code. Okay, any questions or comments at this point? All right, so a couple more quick highlights in terms of Unit 5. I have a bit of stuff in here about, somewhere in here, about using using the warning and the stop functions so that you can write your own code where you issue warnings to users and you stop the code if something is going wrong and issue an error message. I won't go through this in any detail because it's fairly straightforward. But this is the sort of thing that you may need on some of your problem sets, and you'll probably almost certainly need on the final project for the class to be able to write code where you check for conditions, make sure things look okay. If they don't, give back a warning to the user or send back an error message to the user. So that stuff is in here. And then I also have the syntax for using the try statement, which we encountered in problem set 2, so that if you think if you've got some code where something might fail and spit back an error message, but you want the code to continue. Suppose you're in a for loop and you're iterating through a whole bunch of analyses, for example. You don't want an error in one of the analyses to stop your code from executing on the later on analyses. Then it's a good idea to wrap the statement that you think might cause an error in a try statement. And the basic idea here is, just to back up briefly, is this GEV fit function is doing maximum likelihood estimation to fit a statistical model to a given set of data. So it could fail. The maximum likelihood estimate might not converge. There could be other reasons. There could be some problem with a subset of data that you pass into this fitting function, and that could fail. But you don't want that to cause you not to be able to analyze the remaining subsets of your data, say if you're looping through subsets of the data and doing an analysis on each one. So wrapping sort of the key statement, which in this case is this maximum likelihood estimate, or this fitting procedure, in a try statement is a good way to deal with this. And you guys may have used this in problem set 2 if the problem set 2 solutions are up here, and I definitely used it in my solution for problem set 2 to deal with getting to the end of the file. So I think that's all I want to say about this. Any questions before I skip on to Unit 6? Okay. So let's switch over to Unit 6. So we're going to spend a decent chunk of days on this, at least this week and and all of next week, and maybe a little bit into the following week. So the basic idea here is we're going to be talking about how to write efficient code in terms of computational efficiency, how to understand how much memory your code is using and potentially to limit the amount of memory that your code is using. How to understand when R is making a copy of an object and when it's not going to make a copy of an object, and that feeds back into this question of how much memory is going to get used by a given chunk of code. And then some stuff about object-oriented programming and basically about using R to manipulate the language itself, which will come at the end. So I'm going to start off talking about efficiency. And one sort of rule of thumb is, in general, and we've already sort of been encountering this, if there exists functions in R to do something, don't reinvent the wheel. That usually those things will have been written fairly efficiently, particularly if they're part of the core R. And oftentimes those functions will have been written in such a way that they're basically just, the R function is just a wrapper, and it almost immediately calls an underlying C function. So there's not a lot of interpreting of R code going on when that function is being run. Basically it's just a wrapper, and it almost immediately calls compiled C code. And if it's calling compiled C code, that code is generally going to be quite fast, or sometimes it's compiled Fortran code. So if you can use functions that already exist in R, then that's a good idea to do that. So what we're going to talk about now is the sort of mode that I want to sort of be in here is we're going to sort of see some tools for how do you assess how long it takes code to run, and then we're going to see some examples of cases of how you can make your code more efficient. And part of this is basically going to be the idea of just go and play around with something. If you can figure out that this is the slow step in your code, try and do some brainstorming and think about, oh, what are the other ways that I might be able to run this code? And you might have some idea of some of the principles we're going to cover here that suggest that, oh, method A is going to be much faster than method B because we've talked about how R works and method A should be faster. But a lot of times it's just a matter of trial and error. You come up with a few different ways of coding something up, and you then try them out and you time them and you see which one is faster for your particular case. The other comment I want to make is there's an idea in software development, which is that it's a good idea not to try and make your code efficient too early on in the process of developing your code, which is so the basic idea is write your code first without worrying so much about efficiency. Write it so that you make sure that the code works and doesn't have bugs in it. And only then, if you realize that you need to make it faster, would you then go and really spend a lot of time making it more efficient. So that is a good thing to keep in mind. We're talking a lot about efficiency, and it matters, but it's a good thing to keep in mind that you don't necessarily want to start doing this right away. You generally want to get a working piece of code that's reasonable, and then if you need to, think about making it more efficient. Okay, so I'm going to switch over to RStudio here. For some of what I'm doing in this unit, I'm going to have to switch to just plain R instead of RStudio, because sometimes having RStudio sort of in between me and just us and the R session is going to make it hard to figure out what's going on. But hopefully this will work for the moment. So the first thing is just that some tools for doing benchmarking, which is basically seeing how fast your code runs. There's a simple function called system.time, which I think we may have encountered at some point here. So all I'm doing here is I'm just comparing the speed of running I'm going to try and format this a little more clearly here, in keeping with what I said a few minutes ago. Okay, so I'm just going to compare the times involved in, if I have a matrix, I want to figure out what's the mean of the values in each of the rows of the matrix. So I'm going to compare using a for loop to using a function called row means. Okay, so this is a good example of where it's nice to use a built-in R function that will just do this automatically, and where this row means function is basically essentially immediately going to call a bunch of C code. It's going to pass this whole matrix into the C function, and that C function is going to do the looping over the rows. In contrast, we're going to compare that to doing the looping in R and see what the time looks like. But first, I want to take a quick look at the row means function. And what you'll notice when you look at a function like row means oftentimes is that you'll see that it is composed of some pre-processing code here that is often doing a bunch of checking to see what type of object is coming into the function. And maybe it might check the dimensions and things like that and do a little bit of other pre-processing. But then relatively soon on in the code, it's going to go and call a C or a Fortran or a C++ function. And the way that you know that it's doing that is if you see the function .internal or .primitive, or there are a few others. I think I mentioned them in here somewhere. .call, .fortran, anything that all of these things will generally have a dot in front of them and make it sound like they're going and making a call to something that's sort of internal or C or Fortran code. And what that means is that basically don't worry about the syntax of exactly what's going on in here, because it gets a little bit convoluted, and I actually haven't, I wouldn't be able to explain it off the top of my head anyway. But basically, whenever you see this, it means that the objects are getting passed into C, and then everything is getting done in C without the overhead of the R interpreter getting in the way, except for whatever the pre-processing steps are here. So anytime R is doing a whole bunch of interpreting of code, and particularly when it's doing a for loop, it's having to do a whole bunch of stuff that has to do with checking of types and going and looking for objects and figuring out what the values of those objects are, all of the sorts of things that an interpreted language has to do, and there's a ton of overhead involved in that. So what we should see here is that there's a lot different speed between these two manners of getting the row means. And so when we time it, you can see that at times, generally we want to pay attention to the elapsed value here. So we can see in this case that doing it with row means is about 20 times as fast as if we did it using the for loop. The other nice thing about it is if you think about what this code looks like, if you came in, a few of you have some experience coding in C, and so you're sort of naturally accustomed to the idea of if I want to do something where I iterate over a bunch of values, I'm going to write it as a loop, as a for loop. But we've now done enough in R, and many of you came in with R experience to have the sense of, generally in R we want to start out by thinking about using vectorized code. And the advantage is not just speed, and in this case, if this is all we were doing, it really doesn't matter whether it took 0.003 seconds or 0.072 seconds. It happened almost instantaneously from our perspective as a user, so who cares? Obviously, if this were a bigger matrix, then maybe this would start to matter more. But the other thing about this is if you look at this block of code and you want to try and figure out what's going on, you need to read 3 lines of code, interpret what's going on, figure out sort of what the indexing is and how the assignment is going on. Whereas if I see this, it's just totally clear to me right off the top of my head from just seeing it that, oh, what is it doing? There's some object X, it must have rows, and it must be taking the mean of those. End of story. There's sort of nothing else to interpret here. So oftentimes that's an additional benefit in addition to efficiency. Okay, the other, so that's that's sort of very plain vanilla figuring out the speed of something. There's a nice package called rbenchmark, which will do this sort of benchmarking. Once again, this is not formatted very nicely, so it's a little bit hard to see what's happening here. But basically, the way that that the benchmark function within the rbenchmark package works is that it will basically take either one or more R expression, evaluate it multiple times, and take the average of how long it took to evaluate the code. So it will allow you to compare different implementations of a given operation. And also the averaging is nice, and that's what this replications means. The averaging is nice because there's usually some stochasticity here. If you repeat the same operation on a computer, it's not going to take the exact same amount of time every time that you do it. So it's nice to have some averaging to get the law of large numbers working in our favor. So if I set up this, if I load in the rbenchmark package, I can then do something like this. In this case, I'm just going to see how long does it take to compute the cross product of this matrix, which is just x transpose times x. So just a very simple matrix algebra, linear algebra operation. And if I do that, that really should be faster than it seems to be. If I do that, let's say, okay, the elapsed time was 9.3 seconds, and I did 10 replications, so it must be about 1 second per replication. It's a little bit surprising that took as long as it did. I'd have to think about why that is. So sometimes you just want to see how long one piece of code works. So suppose you have some big chunk of code, and you're trying to get a sense for what's the slow step in my big chunk of code. You might want to run something like this benchmark function on some of the lines of code that you suspect of being the slower ones, and then you could see, oh, this one takes this long, but maybe then 2 lines down in my code, that one takes 10 times as long as this. So you can get some sense of relative speeds. But the other thing is you can, if you're in this paradigm that I was suggesting before of you write a piece of code to do a particular operation, and then you know that that's the slow step in your code, and you brainstorm other ways to do it. Now, if you implement it another way, you could directly compare the 2 ways of doing it. So here I'm just doing the benchmark function where I say I'm going to benchmark the first expression, which I'm putting in quotes here because it's a multi-line expression, or putting in curly brackets because it's a multi-line expression, is again that same thing where I'm doing the for loop to get the row means, where I'm looping over the rows. And the second piece, I don't need to put it in the squiggly brackets because it's just a one-liner. So the benchmark is going to compare the speed of this with the speed of that over 10 replications. And this columns argument just controls exactly what the formatting of the output is. You can play around with that if you get a chance. So here we go, and it just gives the result back in terms of, it's a little bit hard to read in this case because it's sort of showing the entire expression as the first thing that it's timing, and then the second thing it's timing is this row mean, so it's a little bit hard because there's sort of not enough space. But we can see that over 10 replications, this one, which was doing the for loop in R, took 0.67 seconds, and this one, which was doing the row means, took 0.05 seconds. So basically confirming what we saw with system.time. Okay, any questions at this point? Yeah, go on.
So you have to want to profile your entire script. Do you have to how do you do that?
Yeah, so you could put the entire block of code in quotes here. That would be a little bit ugly in terms of formatting, right? Another thing you could do is just insert that block of code in a function and then time the whole function call. I think those would probably be the 2 main things. The next thing we're going to talk about is profiling, which sort of gets at that. So maybe that might partly answer your question. Yeah, Jan?
Yeah, so we have one per function. And then one variable is dependent on the calculation of the other, and you want to compare the time of them.
So you have multiple lines of code?
Right. And
Okay.
then you want to compare, let's say, the first 3 and then the last 3.
Yep.
And the last 3 codes depends on the variable the first 3 calculated that you want to see.
Yeah, I mean, you'd probably just need to do 2 separate calls to rbenchmark. One where you time the first chunk and the other where you time the second chunk. But yeah, you wouldn't, and in that case, if it's sort of a sequential algorithm, you probably wouldn't, I mean, I guess if you're trying to figure out which of those two was the slow step, then you might want our benchmark to compare the two of them to each other. But yeah, I can't think of. I mean, I guess you could run the first chunk outside of this benchmarking paradigm and just get the objects you need for the second chunk, and then potentially you could then put the two of them both in the R benchmark. Yeah. Yeah.
So can we compare like multiple approaches? So here we didn't compare two approaches.
Yeah, you could the benchmark basically takes ... as its first argument. So you could after this comma add on a third one and comma and then a fourth one and comma, as many as you want. Other questions? Okay, so the next thing I want to mention is this idea of profiling, and this gets at this idea of how do you find where the slow step is in your code. So I may be able to run this from RStudio, we'll see. So basically, this is a real example in the sense of it's something that I'll often do, the sort of thing I'll often do. So what I'm basically trying to do is generate samples from a random time series. So this is generating samples from something called a stochastic process. So these times here is going to be a sequence of values over time. So I'm just gridding the time dimension here. And then I'm saying this rdist function is basically computing the time lag between all of the pairs of points on my grid. So I'm taking time, I'm gridding time into a set of discrete times. And then I want to know basically what's the time lag between all possible pairs of times here. That's what the next step does. This next step computes a covariance matrix. In this case, it's also a correlation matrix between the value of what I'm basically trying to generate a random time series, and so I'm creating a covariance matrix that's basically a covariance model for time series here. And so this is basically computing the covariance between the value of the time series at any given pair, all possible pairs of points, based on the time lag, the distance between them, and some parameter param. And then I'm decomposing that matrix C, which is a positive definite matrix, into the Cholesky decomposition, which we'll talk a lot about in the unit on linear algebra. So I'm basically decomposing that matrix C into a matrix U, which when multiplied by its transpose gives back the matrix C. And then I'm generating a bunch of random standard normals that are independent of each other. And if I do this step of doing the cross product of that Cholesky factor times a bunch of standard normals, I'm basically generating from a Gaussian stochastic process. And so the result of this will be a vector. And if I look at the values of those vectors and plot them as the y-axis, what they'll look like is some sort of time series. And that parameter param determines whether the time series is sort of really wiggly in time, or maybe it's sort of more smooth over time, or maybe it's really wiggly at a sort of high frequency in time. So basically, this is a function by which I can generate basically these sort of random time series. We'll probably see this again when we talk about linear algebra. I might use this as an example. So the sort of exact details of this for our purposes are not totally critical, but what I want to point out here is there are a few different things that are going on here. We're computing a matrix of distances. We're taking a matrix, this dd, dividing it by a scalar, and then exponentiating all the values. We're doing this Cholesky decomposition. We're generating a bunch of standard random normals, and then we're doing a cross product, which is basically, in this case, a matrix times a vector. So we might be able to think about sort of from a theoretical principle which of these steps should be are probably the slow steps in the code. But we could also just do some profiling and empirically see which are the slow steps. All right, so any questions about the context here? Okay, so here's how we would do this. Turns out that our dist function needs the fields package. So here's what we're going to do, and this is the basic way you use R's profiling tool, which is you call the rprof function and give it a file name, and it's going to sort of write some temporary information out to that file name. And then you call the code that you want to call. This is just a one-liner, but I could have inserted as many lines of code in here as I want. But this calls that make time series function that I just defined. And then whenever my code is done, after one line or however many lines, I call rprof and give it the argument null. And that says, okay, you're done profiling. You can stop now. And then basically we need to call this summary rprof function with the name of that same file here. And basically what it then does is it interprets the output that was put in here and gives it back to us in sort of a user-friendly format. And basically what's happening is the rprof function is basically doing the following as the code is running. It's basically querying R many times in a row, every say 0.01 seconds or something like that, and saying, what function call are you doing right now? And then it waits for 0.01 seconds or however long it says, what function call are you doing right now? And then it waits another 0.01 seconds. So sort of like a kid who's saying, are we there yet? Are we there yet? Are we there yet? rprof is basically saying, what are you doing right now? 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 All that information gets accumulated in here, and then this does the summary of that information to give it back to us. So the fields is a bit of a white herring here. Fields is just because this particular code that I'm profiling uses the rdist function, and that's in the fields package. But fields has nothing to do with profiling in general. It's just this particular example. And so the output we get will look something like this, and I think I'm going to switch over to the PDF because it'll be a little bit easier to see. Okay, so this is exactly the same as what I just showed you. And what it will basically do is it'll show you basically what function call is R spending most of its time in. And it'll do it in two different ways. So there'll be two different blocks here. There's a by self block and a by total block. And the idea of the by total block is I'm going to call a function. That function then calls another function. That function calls another function. So should the time that's being spent in the nested function be attributed to the function from where it's called, or is it just attributed to the function that it's actually in? So the by self is basically doing it as just the time that you're specifically in a given function and not the time that's spent in other functions called from that function. And the by total is basically sort of adding up from the bottom from sort of all the leaves of the different function calls on up. So you can see, well, of course, make time series, the master function, takes up 100% of the total time if I attribute all of the subfunctions time to that function. So it can be useful to look at this in both ways, but if we look at it by self, which is sort of the time spent in each of the specific function calls, what we see is it's spending about 50% of its time in a dot call. So it's doing an internal C call and calling some function via dot call. Turns out it's spending another 28% in a separate call to dot Fortran, which is calling some Fortran code. It's doing a call to the matrix function. It's spending some time in that exponentiation that we saw. It's spending a little bit of time in the division, which is in there. So in some ways this is helpful, but at the same time it's a little bit difficult to interpret because if we go back to our function, we don't actually see the dot call or the dot Fortran in here. So it's a little bit hard to know which of these things is it spending its time in. So at this point, usually we need to sort of go in and start to look in some of these functions and get a better sense of what they're doing. So if I look in, for example, the Chow function, okay, so this turns out this Chow function is just a wrapper that then calls the chow.default function, which we'll see when we get to object-oriented programming. But if I look at the chow.default function, you can see right away basically it's going to some internal compiled code. And it seems like it's calling this LA chow function, which we might or may not be able to see. Apparently not. But if we sort of delve deeper into R, we would be able to see that this call is probably the one that's calling the Fortran code. Well, it's either calling the call or the .fortran. And we'd have to sort of burrow deeper in here to see which of these it's calling. But if we did that, we would get a sense of that. We would get a sense of where that's being called from. We can also look in rdist and see what it's calling, and that might also help us as well. So rdist is doing a bunch of pre-processing, and then you'll notice it is calling .fortran. So sort of by the process of elimination, if we continue in this path of sort of looking at some of these individual functions, what we would decipher is that this 50% of the time is actually being spent in this Chow function, which is the matrix decomposition. which is not surprising because this is an order n cubed operation, as we'll talk about in a few weeks. And about 28% is being spent in the Fortran call that's being called when we compute the distance matrix. And then if we looked a little bit deeper, we could figure out exactly where the matrix function was being called. Although actually, I think that might be called. So there's a matrix call here. We could see there might be other matrix calls in the other lines of code here, but it might be that a fair amount of the time is being spent in this matrix call here, or potentially in additional matrix calls to the matrix function as well.
So will it have anything other matrix? If matrix gone?
Yeah, it should, because it's doing this thing of the sampling, and so it doesn't. I don't think it has any sense of like when it goes into one matrix call and when it's in some other matrix call. So probably all it's doing is it's like, what function are you in? I'm in the matrix function. And then 10 seconds later, what function are you in? I'm in the matrix function. And it has no idea if it's still in the same matrix call or if it's in a different one. So I think it's just adding it up. Other questions? Yeah, Chair?
The output itself add to the timing steps then?
Yeah, so it's sort of like a Heisenberg principle here. The time, this is going to slow down your code because it's going in and interrupting it, saying what function are you in right now. So it is going to affect the time it takes to complete. Yeah. Hopefully, it'll still give you the same sort of relative measure of how much it relatively costs in the different pieces. So I'm not sure. Oh, actually, this. I sort of got ahead of myself because I was saying, oh, how do we even know where .call is called from? If we look at the by total, that will actually allow us to ferret that out a little bit better than just the hand waving I was doing a second ago. So we can see that, okay, 50% is in the .call, but also 50% is in the chal, and I already said, oh, well, chal just calls chal.default, so that 50% just transfers over to chal.default. And the fact that this 48.72 exactly matches here, it gives a pretty good indication that this .call is being done in the Cholesky call, within the chal.default, and presumably within that LA_chal call. And then we could do something similar here in terms of trying to figure out in terms of the .fortran and the rdist and that sort of thing, and trying to sort of piece apart where the different times are coming from. This is actually a somewhat complicated one. Sometimes if you're just writing R code, it's not going to be. It might not be as confusing because you might not have as many calls to these external functions in C, and Fortran, and for that matter. Okay, other questions at this point? All right, so let's skip on ahead. I have a bit more explanation here that you could take a look at. Okay, so I want to turn now to, okay, we've talked some about how could we see where the slow steps are, about how would we time code. I want to turn to actually seeing some of the key things to think about in terms of writing more efficient code. So the first one is that anytime that you use a function like C or cbind or rbind, and you're basically successively adding another piece onto an object, that's going to be really slow. And an example of this, you would never write this code, but I'm just using this for illustrative purposes. But suppose I'm just trying to construct a vector of numbers 1, 2, 3, 4, 5 up through 100. And I don't want to, for some reason, I don't do it with 1:100. I'm doing it this way. Again, this is just for illustration. This is a particularly slow way to do that, which is to say, okay, n gets 1,000. So I'm just wrapping this in a function, but I'm just going to say the first value in x is 1. I'm just going to define that as a vector of length 1. And then I'm going to have a for loop where I successively say, well, x is just the concatenation of the original x, or the current x, with the value I. And then I'm going to return the result. So this would indeed construct the vector 1, 2, 3 up through whatever I use for n, in this case 1,000. But if we think about what is going to be going on under the hood here in terms of how R is doing that, we'll be able to see why this is slow. And I'm going to contrast that just with the simple thing of first setting up a vector x that is of length n, and then sequentially with a for loop filling in the values of that vector. So obviously this is, I've already sort of said, we generally don't want to use for loops to do this sort of thing. But what we're going to see is even this, which we know is not a good way to do this, is much, much faster than doing it this way. So there's sort of gradations of badness going on here. So okay, so we might as well run this, or I guess we can just look at the output here. Well, that's not a very good example. I thought this was much different. Let me try this in RStudio. That should have been even much slower with the it should have been much slower with the first example than the second. So I'm curious what's going on here. Oh, it might be because if I have okay, it probably matters how big the vectors are that I'm creating, which I think is why I have this example of doing it with 1,000,000 here. So you'll notice here this was only about twice as fast to do it in the second manner than the first manner. But here I'm going to do it where I'm creating a vector that's 1,000,000 long and doing the same thing. So if I do this, this is actually probably going to confuse me. What's going on here? Oh, this is just this was to illustrate something different. Sorry. All right, let me go back here and just rerun this with a larger vector. Okay, so let's try this with 100,000 and see what happens. Hopefully I won't have totally undercut my own discussion here. So you can see this is taking a long time, right? So I think that's a good sign that I think what I've been trying to tell you is actually correct. But let's go, while we're waiting for that, let's go back to this code here and think about what has to happen here. So suppose I'm in the middle of this loop, and I have this vector x that's, say, 50 long. Okay? So if we think about what's going on behind the scenes in terms of the computer, R has created this vector that has 50 elements in it, and it's filled up that vector, and this is occupying some particular place in memory on the computer. R has basically asked the operating system for a chunk of memory that can hold 50 elements. And the operating system has provided that chunk of memory, and R has filled up that memory. And so this, whenever R, or for that matter C, or other programming languages are working with vectors or arrays like this, they're always going to have these things be contiguous in memory. So all of the values are going to be stored next to each other physically in the memory on the machine. And that's good because that means you can actually work through the values of the vector very quickly in general. But now if we think about what has to happen here, I have this guy x, and now I say concatenate another value onto x. So I'm trying to put another value basically on the end of x. Anybody have a suggestion as to why that's not going to work very well here?
If it's C, you're going to have to do a whole new memory allocation.
Okay, so if this were written in C, why do I have to do a whole new memory allocation? Well, basically because you've allocated yourself this much memory, right? And if you need something longer, you need to reallocate something that's longer. Okay, so that's basically more or less what's going on here. But let's explore that a little bit more. Suppose that R somehow had a way of putting a value in this next position in memory. What if R did that? Any ideas what would happen?
Overwrite something else useful.
Okay, so this chunk of memory, if we're now thinking of sort of the memory on the machine as being a contiguous piece of memory, the operating system is managing this memory, or the program is managing this memory sort of in cooperation with the operating system. R, for example, has asked for this memory, and maybe R or some other program is using this piece of memory for another value, for some other object, or for something else. So if I were to go, if somehow R were to magically go in and put the next value in here, that could cause the program to crash or all sorts of problems to happen with your computer. So there's no way to just go in and put the value here if the current object is at this length, and that's the length of the object that R knows about and has been interacting with the operating system about. Okay, so given that, basically what Daniel said has to happen is the next time when we come along here and we try and do the C of x and I, to put the next value in here, what R basically has to do is say, oh, if this were 50 long, I actually need something that's 51 long. It's going to go to the operating system and say, give me a chunk of memory that's 51 long. It's then going to have to take these 50 values, copy them into the first 50 elements of the 51 long array or vector, and then put this one in the 51st value. Okay, so that copying is going to take some time. Now imagine, well, what's happening? We're in a loop. We're going to do that as many times as we're iterating through this loop. And so we're going to be doing a ton of copying and a ton of memory allocation. And I think that basically illustrates why when we just did it for 1,000, it didn't matter that much, because we weren't doing all that much copying, because 1,000 elements is not that many. So we'd start out with 1, we'd have to allocate 2 elements, then we'd have to allocate 3, allocate 4, and each time do the copying up to 1,000. But even that's not so bad. This is we have fast computers. But once you get up to doing it, that's interesting. I illustrated this a little bit too much, I think. So let me stop that. Yes, thank you. I'm done here. Thank you. You can see it was taking ludicrously long. So what did I say for n here? So I said 100,000. So somewhere between 1,000 and 100,000, things went terribly wrong, right? So maybe if I do it for 10,000, I'll do this and be able to get a reasonable answer back. But you can see that this thing is it's not growing linearly. That's pretty clear, and that's to be expected given what we just talked about in terms of 1, then 2, then 3, then 4, then 5. You could do sort of the arithmetic to figure out how that's growing and how much more time it should be taking. But now you see when we did it for 10,000, now this is taking 20 times as long to do just the plain for loop where we fill in the already allocated memory versus doing it where we sequentially add on to the end of the object. Okay, so I think that's pretty convincing, even if my first example was not so convincing. And with the 100,000, it's going to be even worse in terms of the ratio of the numbers, which is why it was just basically taking forever to do that one. It's not that the second piece was taking forever; it's that this one was taking forever in the longer example. Okay, so the answer is that in general, you don't need to allocate memory in R. There's not something like in C where you say malloc or new or any of those things that some of you may have heard of. But in these sorts of cases, it is a good idea to create the object in advance. That will force R to allocate memory for the object, and then you can fill in the object as needed or put stuff into the object. So that is precisely what I'm doing here. I'm saying allocate a vector of NAs that is n long, and then fill in that vector. You can do the same thing for matrices. You can allocate the entire matrix, in this case with NAs, and tell it how many rows and columns. Another trick you can do, which is actually even faster, although it doesn't really make a huge amount of difference, is you can actually allocate, you can actually basically create X as a single object, a single scalar value, and then change the attribute that's the length of that to be the number of rows times the number of columns. So that'll basically create a vector that's long enough to hold the entire matrix. And matrices in R are just stored as a single long vector. So you can then just change the dimension attribute of this, what is currently a vector X, and that will essentially change it into a matrix, because a matrix is just a vector with a little bit of additional information about what the rows and the columns are. And you can do similar things with lists. The same sort of thing that we just saw in terms of you never want to do this, which is concatenating successively onto a vector, is you never want to successively add on to a list either. So if you have a list that has 5 elements, you never then want to create a list with 6 elements by tacking the next one on, and then create a list that has 7 elements by tacking another one on, and so on and so forth. And so the equivalent of allocating memory for a regular vector is you can use this syntax which sort of recognizes the fact that in R, lists are also a form of vector. But this is the way you would create a list that has a given length. And this is just an empty list, and you could fill in the pieces of the list as you like. Okay, so we are out of time. Next time we'll talk more. We'll continue talking about efficiency and talk about it in terms of some other aspects of speeding things up.